Welcome to Module 5, Lesson 2, Estimating Probabilities by Collecting Data. Yes, indeed, the whole area of statistics is all revolves around collecting data and then analyzing that data. Okay, so in this lesson, which should be a quick one, we will collect some data. So let's get started. Okay, so here's our example one. It's the Carnival Game. Okay, and here's how it goes. At a carnival, at a school carnival, there is a game in which students spin a large spinner. Okay, at this school carnival, not much fun. The spinner has 4 equal sections. Okay, 4 equal sections, and you can see I've added our little paper clip spinner here again. It's going to be something you're going to need once again, little paper clip spinner. And what happens here, to play this game, a student spins the spinner twice and adds the 2 numbers that the spinner lands on. Okay, if the sum is greater than or equal to 5, the student wins a prize. Okay, now you're going to spin it twice, so whatever, if you get a 1, spin it first time, you get a 1, spin the second time, you get a 3, you add those up, you get a 4. Okay, so that would be your first spin results, okay, or turn number 1, your spin results. All right. Actually, no, I'm sorry. The first spin, and then that would be your sum. I'm sorry, the 5 would be your sum. But anyway, I'll go ahead and fill this table in here in a minute. But what I'd like you to do is to go ahead and find someone to play this so exciting game with, and play it 15 times. As you can see right here, exercises 1 to 8 are going to revolve around your data collection, okay? Because that's what you're doing right now. By making these spins, you are collecting data, okay? And we're talking about probability, and we're going to look at some questions that deal with probabilities as soon as you're done with your 15 spins, or 15 turns, let's say. Okay? Yeah, find maybe you could do it with your mom or dad or sister, brother, friend, or remember, imaginary partner. So, okay, so go ahead and do that. I'm going to pause, and we'll come back and we'll take a look at my spin results. I realize it's a little late to ask you now, but just curious. Here's this probability scale again. I just superimposed this scale. I'll get rid of it in a minute. But remember our probability scale with which started from impossible, which was a 0% chance or a 0 chance, up to certain, which had a probability of what we called 1 or 100%, and then the ones we had in between here, which was were unlikely, equally likely, which was, of course, 1 out of 2, okay, 50-50, and then likely, which was greater than 50-50. So, if, and again, I know in looking at it after you've done it, what might you have predicted on the probability scale of getting a 5 on 2 spins? And yeah, just to think that way. If you think you had 5, how many different sums could you get? Actually, I mean, the sums that you could have gotten 1 plus 1. You could have gotten 2, right? You could have gotten 1 plus 2 in some fashion, which would have been 3. And again, the order of getting these is doesn't really matter. So you can get actually 1 plus 3. Okay, you could have gotten 4, and then 1 plus 4, which was 5. Okay, so it looks like 2, 3, 4, 5 would have been a possibilities with using 1. But then we could have had 2 and 2, which is of course also 4. Okay, so we could just take that one out. That's 4. 2 plus 3, which is 5. And 2 plus 4, which gives us another number, which is 6. Okay, and then using 3. 3 plus 1 is 4, plus 2 is 5, plus 3 is 6. Could have done 3 plus 4, which would have given us 7. And then finally, 4 plus 4, which equals 8. Okay, so these were a possibility. 1, 2, 3, 4, 5, 6, 7. So 7 different numbers. And you think you're doing the 1. You're trying to get the 1 out of 7. But how many different ways are there to get 5? And you had, what you had, 1 plus 4, 2 plus 3. And that's it, really, 2 different ways. But it could have been, you know, first spin, second spin. So 4 different ways. Anywho, if I were to be putting it on a scale somewhere, I would have probably chosen something like this. Maybe equally likely, 1 out of 2. Okay, I'm curious as to what you girls and boys might have thought. But again, that would have been much more interesting or reliable to have actually done that beforehand. Okay, and let me get rid of that. Whoop. Okay, so we're back here again, and some of these errant strokes here. Get rid of these. Clean this up. Okay, let me go ahead, and I'm just going to go ahead and go through what I got on my spins, and here they come. All right, so again, I'm recording this. I got a 4 and a 1. Oop, got a 5. Okay, so I won that round. Well, didn't win that round. Another 5. Okay, so far. Oh, another 5. Oh, another 5. And again, these are all, you know, chance. And again, there's a limited chance here because, I mean, there's only four different numbers on each spinner. Okay, but you know, still chance nevertheless. Okay, 2, 7, 7, so 5, 4, 3. Okay, so you can see I was doing pretty well early on. You can see these last, what was it, 1, 2, 3, 4, 5, 6, 7, 8. My last 8 spins yielded no 5s whatsoever. Okay. All right, so let's go ahead and again, everyone here, it's all gonna look different. So let's go ahead and go to the next page where there are some questions to answer. And again, real quick, this should not take very long. Out of the let's see here, greater than 5. Okay, so out of the 15 turns, how many times was the sum greater than or equal to 5? Okay. Oh gosh, I was talking about it being equal to before, but anyway, yeah. So greater than or equal to, that was the aim. Okay, and in my case, there was 8 outcomes were greater than 5. Okay, 8 outcomes greater than 5. What sum occurred most often? And the truth was that 5 occurred most often for my in my data set. Okay, and what sum occurred least often? 6 and 8 in this sample set. And again, later on, as we delve further into probabilities, we will start calculating more accurately or more precisely the probabilities of different outcomes. Okay, and in this case, I do believe 2 and 8 would have been the least likely to have come up, because a 2 could only be spun or only be achieved by getting a 1 and a 1, and then an 8, a 4 and a 4. Okay, so those were the only 2 ways they could be actually achieved. So a 2 and an 8 would have been in a perfect world, but again, the game of chance is not perfect at all. Okay, so, oh yeah, and I didn't remember this one here, number 4, and it says, if students were to play a lot of games, what proportion of the games would they win? I had a lot of trouble with this idea. Would they win? I would have said, would they have most likely won? Okay, would have most likely won, because there's no definite here. The way they wrote this, they wrote it as a real definite. And again, if we were to look at, what the idea they were getting at was, you're going to use your results here and just say, well, they would have won, if they played a lot of games, they would have won 8 out of 15, okay, 8 out of 15 games. So, I don't agree with that language. Maybe I'm reading it wrong. I'm not quite sure, but I think that question we could just leave alone. I'd be interested to see what you girls and boys said, though. Okay. Next, name the sum that would be impossible to get while playing the game. Oops, I did 2 in a row there. Well, number 5, any sum that would be impossible to get, any sum less than 2, of course, because it's impossible to get less than 2 on 2 spins, or greater than 8. Again, just impossible to get a sum greater than 8. And then the last one there, well, the last one on this page, number 6, what event is certain to occur while playing a game? Well, there's no one particular event or sum which is certain, but it is certain that you will get a sum between 2 and 8 on 2 spins. Okay, that is a certainty. Okay, so when you were spinning the spinner and recording the outcomes, you were performing a chance experiment. Okay? Now, this idea of chance experiment really important in the next few lessons. All right, and a chance experiment is defined. I'm defining it on the bottom here. The process of making an observation when the outcome is not certain. So this idea of not certain, very important, which is, when we talk about probabilities, is the case, okay, most of the time. Otherwise, it would not be very interesting, okay? The area of statistics would not be very interesting if we knew the answer before we actually did the study, okay? Anyway, yeah, so that's what a chance experiment is, and using that word experiment, I mean experimenting. The excuse me, spins of the spinner, rolls of the dice, flips of the coin, could all be considered experiments in this definition, or chance experiments. Okay. All right, and there we go, the chance experiment. Okay, so you can use the results from a chance experiment to estimate the probability of an event. Okay, and this idea of excuse me, estimating, very, very important one. Okay, because we can only estimate the probability when we are doing chance experiments. Okay, these are estimations only. There are no definitives. Again, unless an event is certain. Okay. In the example above, you spun the spinner 15 times and counted how many times the sum was greater than or equal to 5. Okay, so an estimate for the probability of a sum greater than or equal to 5 is right down here. Okay, and they lay it out. This P, okay, is the probability. Okay, and then this in the parentheses there, sum greater than or equal to 5 is exactly what it says right there. Okay, and that equals, so this probability of getting a sum greater than or equal to 5 in this case is the number of observed occurrences of the event, okay, which very simply means the number of times you spun 5 or greater, over the total number of observations, and in our case that was 15. Okay, so number 7 then asks you to go ahead and, for this experiment, playing this game, what is your estimate? And again, they are emphasizing this idea of estimate, okay, which is very different than that question I remember where I was having trouble with. But based on your experiment of playing the game, what is your estimate for the probability of getting a sum of 5 or more? And then for my results, I would put 8 as my numerator, because that's a number of times I did spin a sum of 5 or more. And of course the total number of observations were 15. Okay, And so my results, my probability would be 8 over 15. And as you can see, it's going to be a little bit to the right when we go back and look at that probability scale, a little bit greater than 50-50, so kind of in the equal chance, moving towards the likely part of the scale, the probability scale. Okay, but more or less 50-50 for my results. Now, that's going to be different for yours, and some of you may have entirely different. And maybe some of you got 0. I mean, you could have. 15 is not a lot of tries, or not a lot of turns exactly. I would say that's pretty unlikely that you didn't get 5 or greater at all, but it is still possible, and that's what makes gambling and the stock market so exciting, but also so nerve-wracking, is that things don't always go well. All right. Anyway, let's continue. All right, and just continuing out, I can express my probability as 8 over 15. I could also express it as 0.53 or 53%, and like I had mentioned, just a teeny bit over 50-50. Okay, so number 8 here, based on your experiment of playing the game, what is your estimate for the probability of getting a sum of exactly 5? And again, an estimate, okay? Can't emphasize that enough, all right? No guarantees here. And that would have been 4 over 15, simply because I spun 5, or a total of 5, 4 times out of my 15 tries. And that would have been 0.27 or 27%. Okay? Alright, so example 2 is called Animal Crackers. Alright, and go ahead and read this for you here. Actually, let me go ahead and show you here. Let me read you here. So, a student brought a very large jar. Well, he brought a jar. I'm going to show you a box, but a large jar of animal crackers to share with students in class. So the idea is he brought a lot, okay, and probably a lot more than fit in this little box here, okay, and Barnum's Animals and Crackers, Animal Crackers. These are animal crackers. Some of you may have had these. Yeah, some of you may still have these. These were very popular when I was a child. Animal crackers, they're very, very special little treat to have. I'm not sure if that is the case any longer today. Anywho, let's go ahead, and there they are. These are the traditional animal crackers, the different kinds, and I'm just noticing right now that they don't exactly match up to my little list over here. I do see a lion and a camel. Where's the camel? Got the camel in there? I don't see a camel. Oh well. Anywho, yeah, I guess they weren't going by the Barnum's Animals. But anyway, there are 7 here and there are 7 there, so I'm good with that. Okay, so here we go. So rather than count and sort all the different types of crackers, the student randomly chose 20 crackers and found the following counts for the different types of animal crackers. Okay, so again, he did a random sampling. We've talked about this idea of random sampling, where there is no like controlled way to choose the sample. You just like in this jar, you just kind of close your eyes, stick your hand in, and pull one out. Again, it's random, no guarantee of what's coming out of that jar. All right, so this young person randomly chose 20 crackers and found this count, and here's the count right there on the table. Okay, and what I'd like you to do right now, I'm going to pause and have you pause as well. Go ahead and estimate the probability of selecting a zebra. Okay, and come on back. Okay, yeah, so again, the key numbers we needed here, hold on a second, for our zebra were 3 and 20. Okay, so 3 and 20, because we're trying to estimate the probability of selecting a zebra. All right, so 3 as a fraction, this 3 out of 20, that's what it looks like. All right, so 3 out of 20, and that would equal, as a decimal, 0.15 or 15%. Okay, so we can estimate, and again, estimate only the probability of selecting a zebra based on this sampling, okay, on this random sample this person put together here would be 15%. And if we're going to look on the probability scale and place this event somewhere, we would place it in the unlikely zone, okay, an unlikely zone that you would pick a zebra, as it is pretty substantially less than 50-50. Again, based on this sample only. And again, this is an estimate. Very, very interesting, though. Interesting to do estimates and then to try to, quote-unquote, prove them right or wrong. Maybe we can find some time to do that in class. Okay, so here we go. We have numbers 9 through 15. I'd like you to use what you've learned or what you came in knowing, and go ahead and finish all these. Whichever ones you have some difficulty with, just leave alone, and we can go over them when you turn this on again. Okay, so let's go ahead and take a look here. And our first question we're answering. Okay, so we're going to go ahead and estimate the probability of selecting a lion. Let's go ahead and take a look and see. And there's our chart again. Okay, a chart of data. And a lion I got was 10%, and that was 2 out of 20. Okay. And then we went ahead and looked for the estimate. And again, I'm highlighting estimate just to let you know how important that is to understand that we are just talking about estimating right now. Okay. Selecting a monkey was 420, which was 20%. And then the estimate of selecting a penguin or a camel. Okay, so this one was a little bit different. As you can see, this word "or" is going to be very, very important in the calculations of probability. Or and are very special. Okay, or calls for us to just go ahead and add those two possibilities. Okay, so these possible events are penguin. Okay, penguin here, which is going to be 3. All right, there were 3. Camel was 1. So the word "or" in this case is going to suggest that you could do either of those. Okay, you could in this case we're trying to estimate the probability of either one of those happening. Okay, so if either one of those happens, the possibility of either one of those happening is actually 4. Okay, and that's 1 plus 3, or 3 plus 1. Okay, very, very important, that word "or." Just to let you know, and we'll be talking about this probably a lot more later. "Or" is going to equal addition in this term, so we'll see later. And the possibility of 2 things happening, that is your and that will be will suggest a different operation of math. And again, I won't get into that now. We'll talk about that later. But when you see that word "or," okay, we know we're going to add. All right, so we do add 3 plus 1. And that gives us 4. Okay, 4 over 20, and that's another estimation of 20%, that either one of those will happen. Okay, a penguin or a camel. Okay. Well, a rabbit. I don't see any rabbit. No rabbit on this chart. Okay, so here we go. We have one of our impossible events. All right, and that is on the very far left of our probability scale, on the impossible end of that spectrum. Okay, and it is 0%, of course. All right, so now this question 13 asks, is there the same number of each kind of animal cracker in the large jar? All right, Now, do we know? Can we say with absolute surety that there is or there isn't? No, we cannot. Okay, because again, this is a random sampling. All right, it's pretty unlikely that that is the case, but probably not. Looks like there could be more elephants in this box than the other animals, okay? And again, I said box here, so I was thinking box while I was doing this, but it's actually a jar, okay? Let's correct that. All right, yeah, so it looks like, and that's based on the data that we've collected. And again, statistics is very, very interesting field of math, but it also has its nature is very special because we are talking about probabilities, most likelies, and not about definitive answers. And statistics are proven wrong over and over again. They're misused quite a bit, and we'll talk more about that in the future. But based on the data that we have at this point, okay, it looks like there's probably more elephants in this jar than other animals because of the number that we have they chose 5 out of this one. Okay, number 14, it asks if the student randomly selected another 20 animal crackers, would the same results occur? Okay, and probably not. Okay, results could be similar, but unlikely to be exactly the same. Okay, and this is a very interesting thing, and actually probably a great activity for the classroom. Okay, so to give everyone the same number of items, let's say blocks or cubes or marbles or whatever, and to see how likely or unlikely it is that everyone would pick the same array of colors, let's say. Okay, but probably not. And again, that is the nature of the random sampling or chance experiments. Now the last one asks, though, it kind of ups that sample size, and again, sample size is a very, very important thing in the area of statistics. If there are 500 animal crackers in the jar, how many elephants are in the jar? Now again, they make this definitive statement here, how many elephants are in the jar. I don't like that, okay, or I would rather add, how about this one? Let's say it this way. How about if there are 500 animal crackers in the jar, how many elephants can we estimate there are in the jar? Okay, and if we did that, we had 5 out of 20. We got a likelihood of 25%, 5 out of 20, 25% chance of an elephant being selected. Okay, again, on the unlikely end of the probability scale, but still a better probability than any other animal in this random sample. But anyway, what our random sample showed us, or provided to us, is that the chance of picking an elephant was 25%.